Dissipation of energy. The conduction current, conductivity and resistivity. The electric current. 24. Besides influencing the values of the ether constants as above described, we have also to admit that in certain kinds of matter, when under the influence of electric force, energy is dissipated continuously, besides being stored. These are called electrical conductors. When the conduction is of the simplest metallic type, the waste of energy takes place at a rate proportional to the square of the electric force. Thus, if Q1 be the Joulean waste, Q1 equals K times E squared. And also E times C, if C equals K times E. This new flux C is the conduction current, and K is the conductivity electric. Its reciprocal is the resistivity. The termination, ivity, is used in connection with specific properties. It does not always sound well at first, but that wears off. Sometimes the termination, ANSI, does as well. The conductivity K is constant, or is a linear operator, as in the previous cases with respect to mu and C. The dissipation of energy does not imply its destruction, but simply its rejection or waste, so far as the special electromagnetic affairs we are concerned with. The conductor is heated, and the heat is radiated or conducted away. This is also an electromagnetic process, but of a different order. Only in so far as the effect of the heat alters the conductivity, or, by differences of temperature, causes thermoelectric force, are we concerned with energy wasted according to Joule's law. The activity of the electric force, when there is waste, as well as storage, is E brackets C plus dot B equals Q1 plus dot U. The sum C plus dot B is the electric current, when the medium is at rest. When it is in motion, a further term has sometimes to be added, namely, the convection current. Fictitious magnetic conduction current and real magnetic current. 25. If a substance were found which could not support magnetic force without a continuous dissipation of energy, such a substance would by analogy be a magnetic conductor. Let, for instance, K equals GH. Then K is the density of the magnetic conduction current, and the rate of waste of energy is Q2 equals HK equals GH squared. The activity of the magnetic force is now H brackets K plus dot B equals Q plus dot T. Compare this equation with 10, which was E brackets C plus dot D equals Q1 plus dot U. The magnetic current in equation 13 is K plus dot B. As there is, I believe, no evidence that the property symbolized by G has any existence, it is needless to invent a special name for it or its reciprocal, but to simply call G the magnetic conductivity. The idea of a magnetic current is a very useful one, nevertheless. The magnetic current .B is of course real, it is the part K that is speculative. It plays an important part in the theory of the transmission of waves in conductors. Forces and fluxes. 26. So far we have considered the two forces, electric and magnetic, producing 4 fluxes, 2 involving storage and 2 waste of energy. And we have defined the terminology when the state of things at a point is concerned. We reckon forces per unit length, fluxes per unit area, and energies or wastes per unit volume. It is thus a unit cube that is referred to, whose edge, side, and volume are utilized. But a unit cube does not mean a cube whose edge is 1 centimeter or any other concrete length. It may indeed be of any size if the quantities concerned are uniformly distributed throughout it, but as they usually vary from place to place, the unit cube of reference should be imagined to be infinitely small. The next step is to display the equivalent relations, and develop the equivalent terminology. When any finite volume is concerned in those cases that admit of the same simple representation in the form of linear equations. Line integral of a force. Voltage and gaussage. 27. The line integral of the electric force from one point to another along a stated path is the electromotive force along that path. This was abbreviated by Fleming-Jenkins to EMF. He was a practical man, as well as a practician. When expressed in terms of a certain unit called the volt, electromotive force may be, and often is, called the voltage. This is much better than the volts. I think, however, that it may often be conveniently termed the voltage irrespective of any particular unit. We might put it in this way. Volta was a distinguished man who made important researches connected with electromotive force, which is, therefore, called voltage, whilst a certain unit of voltage is called a volt. At any rate, we may try it and see how it works. The line integral of the magnetic force from one point to another along a stated path is sometimes called the magnetomotive force. The only recommendation of this cumbrous term is that it is correctly correlated with the equally cumbrous electromotive force. Magnetomotive force may be called the Gaussage, after Gauss, who distinguished himself in magnetic researches, and a certain unit of Gaussage may be called a Gauss. I believe this last has already been done, though it has not been formally sanctioned. Gaussage may also be experimented with. The voltage or the Gaussage along a line is the sum of the effective electric or magnetic forces along the line, the effective force being merely the tangential component of the real force. Thus, electric force is the voltage per unit length, and magnetic force the Gaussage per unit length along lines of force. Surface integral of a flux. Density and intensity. 28. Next, as regards the fluxes, when considered with reference to any area. The flux through an area is the sum of the effective fluxes through its elementary units of area, the effective flux being the normal component of the flux or the component perpendicular to the area. We do not, I think, need a number of new words to distinguish fluxes through a surface from fluxes per unit surface. Thus, we may speak of the induction through a surface or through a circuit bounding it, or of the current through a surface as across the section of a wire, or of the displacement through a surface as in a condenser, without any indefiniteness, meaning in all cases the surface integral of the flux in question. In contradistinction to this, it may be sometimes convenient to speak of the density of the current, or of the induction, or of the displacement, that is, the amount per unit area. Similarly, we may sometimes speak of the intensity of the electric or magnetic force, using density for a flux and intensity for a force. It may be observed by a thoughtful reader that there is a good deal of the conventional in thus associating one set of vectors with a line, and another set with a surface, and other quantities with a volume. It is, however, of considerable practical utility to carry out these distinctions, at least in a mathematical treatment. But it should never be forgotten that electric force, equally with displacement, is distributed throughout volumes, and not merely along lines or over areas.